Hi, this is a video starting to talk about stoichiometry. So, stoichiometry is when we can study the kind of numerical relationships between reactants and products in a balanced chemical equation. So, key here is that you have to have a balanced chemical equation, and then we're going to use the coefficients as moles. It is based on the law of conservation of mass, just like balancing chemical equations. And we know that the total mass of the reactants and products are equal during a reaction. So, anyways, we have something called a mole ratio. I call this the mole-mole ratio because you'll have mole and mole in the numerator and the denominator. And it's a conversion factor that's going to help you convert between any two substances in a balanced chemical equation. So the difference, what we're learning right now is that we can look at a coefficient, like there's a 1 here for the propane. We can also interpret that now and say 1 mole of propane, 5 moles of oxygen, 3 moles of carbon dioxide, and 4 moles of water. So we can write a mole-mole or a mole ratio. For example, this one, I'm going to do carbon dioxide and oxygen. So I can only compare 2 at a time. So 5 moles of O2 for every 3 moles of CO2. So that's what a mole ratio is. It's the moles of 2 of the substances in a reaction. And then just know that you can write it either way, and that'll depend on what you're converting. So if you try, another example is looking at carbon dioxide compared to water. So our mole ratio is going to be 3 moles of CO2 for every 4 moles of water, or I can reverse it. And then what we're going to do now is, if you could grab your pink sheet, we are we are going to use that mole ratio in the middle here. So it'll always be the moles of B, which is what you're trying to solve for. This is your unknown, over, and I'm putting little boxes here because it depends on the balanced chemical equation what the numbers are going to be. But A is whatever you were given in the question. And then I would add Avogadro's number. We're going to use that again, and molar mass. So I'll show you eventually. Like, it's possible that you'll know the grams. Like, let's say I know the mass of the propane from that balanced equation. I would convert to moles of propane, and then I could do a mole ratio and convert it into moles of water. Then I could use the molar mass of water to get the grams of water. And those are the kind of examples I'm going to show you in just a minute. So this is actually broken into 2 lessons in the book, but it's really kind of goes all together. So to do the stoichiometric calculations, they're similar to what we've been doing. We're still going to use dimensional analysis. So here is that same reaction of propane combustion. And in this question, we have 10 moles of propane, and we're wondering how many moles of CO2. So just like we've done with the mole conversion, we're going to start with our given number, which is propane, 10 moles. And I definitely recommend that you write the substance, because that's one of the things that can get confusing, is just keeping track of which thing you're talking about. So I'm really right here at mole, and I'm going to switch over and use my mole-mole ratio to moles of the other compound, which in this case is CO2. So I'm going to say 3 moles of CO2. I'm getting that 3 right there for every 1 mole of propane. So my answer then is 30 moles of CO2. So that was the simplest type of stoichiometry problem, where it's just moles of one using that mole ratio to convert to moles of another substance in the reaction. Now we can talk about some that are not just plain mole to mole problems. So in this problem, we have 1.25 moles of chlorine, and then we want to know the mass of the sodium chloride. So these are my two that I'm interested in. So starting with 1.25 moles of chlorine. So I'm right here. I'm going to convert over to moles of sodium chloride, and then I'm going to use molar mass to get to grams of sodium chloride. So right away, I'm going to do a mole-mole ratio. So 2 moles of sodium chloride. I'm getting that 2 right here. For every 1 mole of Cl2, there's a 1 right there. So that got me here. Now I'm going to use molar mass. 58.44 grams of sodium chloride are in 1 mole of sodium chloride. So notice, how did I get that 58.44? I took sodium and chlorine. There's 1 and 1. Then I look on my periodic table, and then I just add those, and I'll just double check that I got the right number. So 22.99 plus 35.45 is then 58.44 grams per mole. So notice I did not multiply this by the 2. I'm already using the 2 right here. So when I do molar mass, it's still always for 1 mole. So then when I calculate this, I'm going to get, whoops, I just got an error. I want to think about my sig figs and my unit, and I get 146 with 3 sig figs grams of sodium chloride. So just a reminder, the moles that are in the mole ratio have infinite sig figs. So really, I'm only looking at my starting 3 sigs, and I'm going to end with 3. So we'll continue. Here's another problem, and this is, the compound ammonium nitrate, which is used in fertilizers, will decompose according to this reaction. So in the question, they're telling me I have 25 grams of the ammonium nitrate, and they want me to know how much grams of water am I going to produce. So really, I'm starting over here. I'm going to move to moles. I'm going to do a mole and switch to moles of the water, and then I'm going to use molar mass to get to grams of water. So this problem is going to have 3 conversions. So 25 grams of ammonium nitrate, and I know that I'm going to need 3 of these. So sometimes it's helpful to just write those out so you remember that you're going to need to use 3. So the first one I'm going to use is I need the molar mass of the ammonium nitrate, which I need to quick do. And then, so I get 80.06 grams of ammonium nitrate for every 1 mole of ammonium nitrate. So that gets me here with my moles. Now I'm ready to do that mole step, and I'm going to use 2 moles of water because I'm trying to convert over to the water for every 1 mole of ammonium nitrate. And then I'm right here. Now I'm going to use the molar mass of water, which is 18.02 for 1 mole of water. So notice I'm not multiplying that by 2. And then when I calculate it with my sig figs, I should get 11.3 grams of water. And